All right, let's look at the process of water boiling. Liquid water going to gaseous water. If we look at this particular process, what's going on with the change in enthalpy and what's going on with the change in entropy? With the change in enthalpy, I hope you see that I'm going to have to put energy into liquid water as heat in order to get it to boil. So we know that the enthalpy change is going to be positive. In terms of the entropy, I'm going from liquid water that's, concentrated, say, in a glass, and when we boil it, boy, that water, that's going to spread all over the place. So in terms of the entropy change, well, that's also going to be positive. But in terms of whether they're favored or not, the entropy change, that's going to be favored because we're taking matter that's concentrated and spreading it out. In terms of the enthalpy, it's the other way around though. We're taking energy that's spread around in the surroundings and we're concentrating it into the system. So this is disfavored. So the entropy is favoring the process, making it more spontaneous, but the enthalpy is disfavoring the process, making it less spontaneous. So how do we figure out which way this is going to go? Is it going to be spontaneous or not spontaneous? Well, there's another thermodynamic function that we can use to help us figure out what's going to happen. And that thermodynamic function is simply temperature. It's that simple. We put these three thermodynamic functions together, and that's going to help us determine whether the process is going to be spontaneous or not. And we use it in the following equation. We have a new thermodynamic function called the Gibbs energy. And the Gibbs energy combines these three thermodynamic functions. It looks like this. The change in the Gibbs energy is the change in the enthalpy minus the temperature times the change in the entropy. And all of these refer to the changes occurring in the system. It's slick. Now, in terms of the Gibbs energy, it works out that if delta G is negative, then the process is spontaneous, as written in the forward direction. It's going to happen by itself. You don't have to do anything. It is going to happen. If delta G is positive, then the process will not happen on its own. It is non-spontaneous. Now, it might happen if you, kick it, give it some energy, do some stuff to it, but just sitting there on its own, nothing's going to happen. So let's apply this equation to this process using values that we can find in Appendix L in your text. So here's Appendix L, and you can see here at the top we have the standard enthalpy of formation. Hey, look, they have the standard Gibbs energies of formation, and they also have standard entropies. And we go down and we can look what these values are for liquid water, and we can look at what these values are for gaseous water. I want you to pay attention to the units. The changes in enthalpy are kilojoules per mole. That's the same as the Gibbs free energy. The entropy is different. The units of that are joules per mole per Kelvin. You've got to pay attention to this. But what we'll do first is we'll look these values up, which I've already done, and we're going to do some calculations. All right, so here we've got liquid water, and we've got gaseous water, and I want to know the standard Gibbs free energies for these substances. Those will be in units of kilojoules per mole. I want to know the standard entropies in joules per mole per Kelvin. And I want to know the enthalpies of formation. These are also in kilojoules per mole, similar to the Gibbs free energies. For liquid water, these values are negative 237. The standard entropy is 70, and the enthalpy is negative 286 kilojoules per mole. For gaseous water, the Gibbs free energy is negative 229. The entropy, standard entropy, is 189, and the enthalpy is negative 242. So now what I'm going to do is I'm going to go ahead and I'm going to calculate the change in enthalpy for this particular reaction. What reaction? Well, let's remind ourselves we're going to do it for the boiling of water. So that's liquid water going to gaseous water. And the change is going to be, well, that's going to be the final condition minus the initial condition, right? And so let's see, final is gaseous. That's negative 242. Of course, this is all kilojoules per mole, and I need to subtract from that the initial condition, which is liquid water. That's going to be a negative 286. So what's that come out to? So this is positive, yeah? So let's see, 242, make it negative, and we're going to add 286. So that's a positive 44 kilojoules per mole. Does that make sense? Let me just think about that. Yes, I'm boiling water. That's endothermic, so that better be positive. So that's delta H. Let's calculate delta S for this particular reaction. Well, that's going to be the final entropy minus the initial entropy. Let's see, final, that's gaseous, which is 189. And these are units of joules per mole Kelvin. And I've got to subtract the initial entropy, which is the entropy of the liquid. That's going to be 70. 189 minus 70. I should be able to do that in my head, but I'm just going to do it here. Make sure I got it right. That's positive 119 joules per mole per Kelvin. Let me see if this makes sense. I'm boiling water, and that's a positive entropy. That makes sense. This is more probable. Stuff's more spread out. Now I can use delta G equals delta H minus T delta S to find out what is the entropy change of this process under standard conditions. That's what that circle means there. And you should know that standard conditions, so if we see some symbol at standard conditions, that means at 298 Kelvin, that's about room temperature, and 1 bar pressure. So that's about atmospheric pressure. So under normal conditions, is the boiling of water going to be spontaneous? Well, think about that. Does water boil at room temperature and atmospheric pressure? No, it doesn't. So because of that, I'm going to expect this to come out to be positive when I'm done. Because let's remember, delta G positive, that's not spontaneous. Delta G negative, that is spontaneous. Let's see if it makes sense. Boy, I hope it does. Okay, so what was my delta H for this process? That was a positive 44. Oh, this is joules, that's kilojoules. So I'm going to make it 44,000 joules per mole, because I want these units to talk to each other. Now I'm going to have to subtract from this the temperature, which is going to be 298 Kelvin. That's the standard conditions, times 119 joules per mole per Kelvin. Kelvin cancels per Kelvin, and my units will be joules per mole, which is good, because that's what this is. So let's figure out what that is. 298 times 119. So let's see, my delta G is positive 44,000 joules per mole. And that's going to be minus 35,462 joules per mole. So let's see, let's just subtract that from 44,000. 8.5 kilojoules. Positive. 8.5 kilojoules positive, delta G is positive, and so we would expect this to be a non-spontaneous reaction at 298 Kelvin. Well, let's just see. Let's see what it would be. We can calculate delta G, right? We can do that. Actually, we can do that right here. So let's see. Delta G, according to the tabulated values, that's going to be, my final minus initial. So it's my final. Gas, negative 229, minus my initial, which would be the liquid. I've got to add those. These are kilojoules per mole. So let's see. I can do it like this. 237 minus 229. Hey, look at that. 8 kilojoules per mole. That is just beautiful. That's just gorgeous. Look at that match. And of course, it's positive as well. And so we see that the boiling of water at room temperature is not considered to be spontaneous. You want it to boil, you got to put energy into it. Stick it on the stove, increases temperature.